We'll get started. So today we're going to talk about properties of the chemical bond. This is sort of just a brief video that we need to know to help broaden our understanding of bonding once we start, once we finish up here with Lewis dot structure and start talking about the 3D geometry of molecules. All right, so one of the properties of a bond is the so-called bond order, and this is a representation of the bond strength. We calculate it by taking 1/2 of the bonding electrons, and the larger the bond order, the stronger the bond. So let's look at this example here. This is a Lewis structure. The structure is a valid Lewis structure, right number of electrons, octet around everything. Hydrogen has its sort of effective octet of 2 around. Well, let's calculate the bond order. Here's some symmetry here, so we get this all at once. Bond order here, this bond, 1/2 of 2 is 1, bond order of 1. Likewise for this one. Now this one, bond order is 1/2 of 4, which is 2. Now it really is as simple as looking at the Lewis structure and seeing whether there's 1 line, 2 lines, or 3 lines to give us the bond order. Now, as we've learned about resonance structures, then bond order can take on non-integer values, and we have say atom A and atom B, and we have a bond and a dash, and that dash could represent any value from 1 to 2, so like a bond order of 1 to a bond order of 2, everything in between. And it is just the average of the individual bonds in the resonance structure. Now, as I said, bond order is tells us a bit about the energy. And as we expect, as bond order goes up, energy goes up. But very important point here, it does so sublinearly, meaning that the bond strength of a double bond is a single bond. And the bond strength of a triple bond is not 3 times as strong as a single bond. And this has something to do with the way the electrons are distributed in a bond as we compare a single bond to a double bond to a triple bond, which we'll be coming to in the next few lectures. Now, another aspect of a bond that we want to talk about is bond polarity. And we define that based on the electronegativity. And we've mentioned electronegativity, and you've read about it in your periodic trends, but we can look up the electronegativity for any atom in a bond. So let's go ahead and redraw this. And if we look this up, it's 2.1, 2.5, 3.5. And what we do is we look at any individual bond, and we look at the 2 atoms involved, and we calculate a delta chi-el. This is electronegativity. This is the change in electronegativity. So for this bond here, the carbon-oxygen double bond, that's going to be 3.5 minus 2.5 equals 1. And then for the carbon hydrogen bond, that's 2.5 minus 2.1, which is 0.4. Now, what do these numbers mean? Well, there's kind of a sliding scale here from an ionic bond in which it's a complete non-sharing. One takes a full electron and the other gives up that electron, all the way down to nonpolar covalent. So we know a covalent bond is when electrons are shared. Completely nonpolar covalent bond means the sharing is equal. And this pretty much happens only when the 2 atoms are the same, although there are some elements with very similar electronegativity. So if that's the case, then we would have a completely nonpolar covalent bond. And then somewhere in the middle here, we have a polar covalent bond. Now, what's what? How do we get that from the electronegativity? Well, there's a general rule of thumb, and remember here, this is a sliding scale, a continuum, but what we typically say is that 2 or higher in a difference that will be an ionic bond. And then below 0.5 will be a nonpolar bond. And then everything in between will be a polar covalent bond. So we would recognize this as being 1. This would be polar covalent. This is 0.4. With this rule of thumb, we would call this nonpolar. But of course, it's slightly polar, right? Now, we indicate this in pictures on the Lewis structure. By using a delta and a negative for so-called partial negative charge. We don't have a full electron sliding over, but partial electron, and then a partial positive on that carbon. Now note, this is for an individual bond. If we say, okay, this is nonpolar, but it is slightly polar, then this would be delta plus, and the carbon here, right, would be delta minus. So in this same molecule, with the oxygen, carbon is a partial positive. With the hydrogen, it would be a partial negative. Now, because this is stronger, it overall is partial positive. And that's what's important in impacting the chemistry. And that's a big portion of understanding organic chemistry, is what parts of the molecule are partial positive and which parts are partial negative. All right, so this is just a few examples of some auxiliary information surrounding chemical bonding and associated with the Lewis structures. And so this will help inform us when we start talking about the 3D geometry and trying to decide whether a molecule overall is polar or nonpolar.